Hello. From previous discussion, we come to know that heat is a transfer of internal energy from one part of the system to another part due to the difference in temperature. Where there is a temperature difference, it is obvious that the internal energy flow from higher temperature to the lower temperature area. So this is known as heat transfer. So there is three mode of transfer of heat, that is conduction, convection and radiation. When solid are heated at one end, heat travels due in course of time to the other end. It is because of this reason when we place a metal rod over a flame, we feel the other end is heated up. The phenomenon of transfer of heat energy from one part of a solid to another part at a lower temperature without the actual motion of the molecules is called conduction. In this case, what happens? The molecule of a higher temperature area transfer energy to the molecule uh, near to it. So only heat energy is transferred from one molecule to another uh, with respect to the difference in temperature. So there is no actual motion of molecules takes place. Molecules are in its position, fixed position. So only heat energy flow from one end to another. This is known as conduction or thermal conduction. So the material which conduct heat from one end to another are called good conductor of heat, and those material which do not conduct heat from one place to another or one end to another are called bad conductor of heat. So the amount of heat flow with respect to time is directly proportional to the area of the face of the conductor. Whatever is the area of the face. For example, for circular rod it is pi r square, and for rectangular rod it is a product of length into breadth of the rectangular slab or rectangular rod. So, rate of flow of heat with respect to time is directly proportional to the area of the face of the conductor, and it is also directly proportional to the temperature difference. If temperature difference is large, then rate of heat flow with respect to time will be greater, and if the temperature is low, then slowly heat flow with respect to time. But the rate of heat flow with respect to time is inversely proportional to the thickness of the rod or thickness of the slab. So we got three dependence, that is rate of heat flow with respect to time is directly proportional to the area of the face of the conductor and temperature difference, but inversely proportional to the thickness of the slab or rod. So if we write the equation of proportionality, then we get the proportionality constant called thermal conductivity. The rate of heat flow, that means flow of heat with respect to time, is called heat current. It is denoted by H, and the final expression for heat current is equal to K. K is the proportionality constant, which is called thermal conductivity, change in temperature and or difference in temperature by length of the rod or thickness of the slab. So SI unit of thermal conductivity is joule per second per meter per Kelvin or watt per meter per Kelvin. So higher the value of K, that is thermal conductivity, the more rapidly or at high rate heat conduct from one end of the rod to another. So it depends upon the substance nature of the substance, and the value of thermal conductivity in solving numerical problems are given in the book, as well as we will found the value of thermal conductivity value in question papers also. So, from the expression of heat current, we can define thermal conductivity. It is defined as the amount of heat flow in 1 second through 1 meter square area of a length of 1 meter through temperature difference of 1 Kelvin is called thermal conductivity. That means if we consider a rod of length 1 meter, of area of cross section 1 meter square, and if there is a temperature difference between the two ends of the rod is 1 Kelvin, then the amount of heat flow through that rod is called the thermal conductivity of that given substance. It varies with nature of the substances. Higher the value of thermal conductivity, that means the substance is the best conductor of heat. Example, silver is the best conductor of heat, and poor or less the value of thermal conductivity, that means the substance is a bad conductor of heat. Now, the second mode of energy transfer is called convection. What is convection? In this mode of energy transfer, once a particle gets heated, those particles moves away from the source of heat and energy, and they share energy to the colder particles. Due to the actual movement of the particle, there is a vacant space created in the system, and that vacant space is taken by the colder particle. Now that a portion of colder particle also gain heat energy, and those molecules also move away from the source, and the process will continue. The colder particle again take the vacant space of the heated particle. In the laboratory or in the closed system, this process will goes on. In natural condition or in nature, what happens? Gravity plays an important role here. When a particle or fluid is heated from below, the hot part expands and therefore become less dense. Okay, because of buoyancy, what happened? The less dense material get rise from lower part of the system, and the colder part where it is above the heated particles, the colder particle will take the space through this. They cover the vacant space or replace it. This is again heated, gets heated and rise up, and again colder particle will take the vacant space. This process goes on. Okay, this process goes on. This mode is called conduction. And convection involves bulk transport of different part of the fluids. We can say liquid particle or gaseous particle. So we can say example of natural convection as a sea breeze or land breeze. In sea breeze and land breeze, this phenomenon takes place, and we also get trade winds which flows from heated gas or wind moves from equator to a certain altitude, and there it gets cold, and after that again it returns to the equator. That is trade wind. So these are the two examples of convection in nature. The third mode of transfer of heat is radiation. The best example of radiation is that Earth receives heat energy from sun. The sun emits heat energy and it flows through the vacuum, through the atmosphere, and we receive heat energy on the surface of the earth. In this there is no need of medium. That means without any medium, heat flow from source to the absorber. So all bodies emit energy, radiant energy, whether they are solid, liquid, or gas. The electromagnetic radiation or heat radiation emitted by a body by virtue of its temperature uh, is called thermal radiation. Okay, when this thermal radiation falls on other bodies, it is partly reflected and partly absorbed. The amount of heat that a body can absorb by radiation depends upon the nature of the or color of the body. An object or a body which can absorb all the possible wavelengths of the radiation incident on it is called a black body. As there is no reflection, so we cannot find any light from that object, so we will see only black color. That means if there is no any color, then we can say the object is black. So that object which do not reflect any wavelength of light or any wavelength of the electromagnetic spectrum, then the body is called perfectly black body, perfect black body. That type of body can absorb all possible wavelengths, as well as it emits all possible wavelengths also. When it is left for cold in a cold place or without heating, then that object or that body can emit all the possible wavelengths also. Therefore that type of object or body is called perfect black body. Thus the radiation emitted by black body is called black body radiation. So if we draw a curve between radiated energy per unit area per unit wavelength by black body versus that wavelength at different temperature, we will get such type of curves. So wavelength and absolute temperature relation is given by Wien displacement law. This law is useful to calculate the surface temperature of celestial bodies such as sun, moon, and other stars. So the most important features of black body radiation is that they are universal. They depend only on the temperature of the material or the temperature of the black body, irrespective of the nature of the material. Size and shape of the black body. Electromagnetic energy radiated by a body or an object is directly proportional to the size of the object, its capacity to radiate, that is emissivity, and absolutely the temperature of the material. A perfect radiator, the heat and energy emitted per unit time is expressed as. So the expression is H equal to A sigma T to the power 4. So A is the area of the body, T is absolute temperature, it is with power 4, and sigma is the proportionality constant called Stephen's constant, and its value is 5.67 into 10 to the power minus 8 watt per meter square, Kelvin to the power minus 4. So this relation is called Stephen-Boltzmann law. This is called what? Stephen-Boltzmann law. So from this expression, for a general body, that is, which is not a perfect black body, in that case emissivity factor comes with this expression. So H is equal to A epsilon, or in textbook it is a small letter e. I am using here epsilon. So A epsilon sigma T to the power 4, where epsilon is the emissivity of the body or emissivity of the object. So for a perfect radiator, that means which can radiate all the possible wavelengths of electromagnetic radiation or electromagnetic wave, then its emissivity is equal to 1. Otherwise, for a tungsten lamp or tungsten wire, emissivity is 0.4. Similarly, for other materials we can find in the appendix of the textbook. So further, if a body at temperature T, and its surrounding is Ts or Ts, then we can write the expression for a radiator is equal to H equal to sigma A, T to the power 4 minus Ts to the power 4, where T is the temperature of the radiator or body and Ts is the expression for surrounding temperature.